objects which are being processed right now will be gray, and the objects which cannot be reached at the end of this algorithm are actually unreachable objects. So we can kick them out and free up memory. So taking an example, if you have this graph, nodes A to G, and you want to run the tricolor algorithm with a BFS, which is breadth first search, you need a queue. So you push A into the queue, and this is how the traversal will be. So at the end of it, you see that because there is no outgoing edge, or rather no incoming edge to F, we were never able to process the node F. And that's the reason why it stayed white. And at the end of it, those two nodes are gone. With a stack, this is how it actually happens in real life, because you want to avoid all that processing nodes in a queue. So the stack goes deeper. A, B, C, D. Oh, before D, actually C runs out of all the nearby nodes. There's no outgoing nodes from C. So you mark it as processed black. The current stack has A and D. So those nodes are being processed, and we are not sure about D, E, F, and G. That's how the algorithm works. And once you're done with the processing, you have the same result. Okay, so we have a way of identifying garbage right now, but we need some sort of tricks and optimizations so that we can pick up garbage even faster. And here comes the generational hypothesis. This was, I think, originally quoted in the 1983 paper by Brook, unless I'm mistaken, or 1984 also. There are papers on this which talk about if you partition the heap on the basis of not their not size, but their behaviors, then you can make a lot of optimizations. Basically, you have objects which are young and objects which are old. You partition them in terms of their property of young or old. And then you notice that most young objects tend to die early. So that means that if I have a room full of babies and I have a room full of middle-aged people, and I periodically poll the room full of babies, I'm likely to get dead bodies over there, which I can clear up. So I'm going to be reclaiming the memory, and that's good for me. So I'm going to be polling that room more frequently, let's say every day. While if I poll a room full of middle-aged people, in the time of coronavirus, this is even more relevant. It's less likely for them to pass away. So on that happy note, we are going to be accepting this generational hypothesis for most of the algorithms that Java has, except for the very recent ones. And we'll see how this affects us. But before we move on, can anyone give me an example of an application which does not follow the generational hypothesis? Anyone on the chat? You can type your answer here. Okay, I'll give an example. Oh, thread pool. A thread pool. Yes, when you have an object pool, there is a limited number of objects you can have in that pool. So most likely what's going to happen is before you can collect it, you actually want to keep it around. So that's a good example, yes. There's a couple of more, a queue, yes. Jacob, that's something that I was looking for. That's a great answer because I was looking for it. So awesome. One of the common examples is, one of the common examples is a cache. So a cache has a limited number of objects, and the least recently used are the ones which are pulled out. So if we look at the generational hypothesis, what it says is that the older objects need to be most likely kicked out first, while that's not true for the algorithm that we are choosing, right? There's another example of a queue that we'll be looking into. Yeah, Anidor, I'm sorry, I might be getting the pronunciation wrong, but sessions in browsers are killed after a timeout, but they are usually old sessions. Yes, and also we'll look at the queue example right now. Okay, so let's take an example of this doubly linked list. It's a queue. So what's happening here is that you have each object pointing to the next object and also a previous pointer. After a few garbage collection cycles, we are going to be promoting 1, 2, and 3 to the old graph, to the old heaps area. And then we figure out that 1, 2, 3, and 4 are dead. So the front of the queue has now moved to 5. These objects are dead. But the strange thing here is that 4 should be collected. 4 is in the young generation, and it should be collected. But it's not being collected because it has pointers from the old generation pointing to it. So what's happening here is that, I mean, this is a single object, but if you have an application in production, you could have hundreds or thousands of elements in the young or Eden space, which are not being collected because you have these older objects pointing to them and keeping them alive. And eventually what's going to happen is that 4 is also going to get promoted, because after a few garbage collection cycles, you see that, oh, 4 is not getting collected. It's an old guy, it's an old timer, send it to the old generation. And then what? 4 is pointing to the rest of the elements. So this is a problem. This is a place where the generation hypothesis doesn't really fit in very well. And this is called nepotism, which is basically you're being promoted without having the necessary requirements of actually being promoted. But we are going to be assuming that the generation hypothesis holds for most cases. So if you're creating as generic as possible garbage collector, we need this. So we partition the heap on to 2 pieces, young generation, old generation, and then the young generation is further divided into the Eden space. This is, I think, from the Bible, where the starting objects are sent over there. And then you have 2 survivor spaces where objects, if they survive a few garbage collections, they are sent over there. So a demo, you have the Eden space, objects 1 to 6. The ones which survive after the first garbage collection are sent to a survivor space, and they're marked as, these guys are survivors. So survived 1 garbage collection cycle. Similarly, after the second garbage collection cycle, you have some compaction also happening. That's the reason why you have 2 survivor spaces. But at the end of it, you have 3 objects in the survivor space. And if you keep doing this, after a certain point of time, you're going to say that these objects are really important. They have survived a lot of garbage collection cycles. Therefore, we are going to be promoting them to the old generation. So this is great. There's one interesting thing here, though. The old objects, they also, if a object is picked up from the Eden space as being worthy of being kicked out, we have to look at old generation pointers also. So let me take an example. You have 1 to 6 in the Eden space or in the young generation, and the old generation is empty. 2 objects survive after the first garbage collection. And let's assume that object 3 and 5, which were considered white in the original tricolor algorithm, basically they have to be picked up by the garbage collector, are now being pointed to by an old object. So we can't pick these objects up because they are being pointed to by an old object. If it tries to reference that object, it's going to throw a null pointer exception. So what we need to do is we need to have some information that, hey, is old object number 2 pointing to 3 and 5, right? And if it does, then, well, mark them as white. But the problem here is that it completely nulls the use of breaking the heap into 2 regions of old and young. Because the reason why we broke it into 2 places is because we were polling the young region very frequently, while the old region had infrequent polling. If at every young generation, you have to go back to the old generation and ask that, hey, is anybody pointing to the young guys over there? And you have to basically go through all the objects in the old generation. It defeats the purpose. So can anyone tell me what is the solution for this that is applied in Java? The main problem is that you have young objects being pointed to by old objects, and you don't want to be going through all the old objects to figure out which young objects need to be kept alive. This is not vodka, by the way. Okay, solution coming in 5, 4, 3, 2, 1, 0. Okay, so we have a data structure. So even before that, the problem is that when an old generation object starts pointing to a new generation object, we need to take note of that. If we that we have to later on look into in the garbage collection cycle, then we are safe, right? So for example, if you had a room full of babies and baby number 3 and 5 have the same parent, which is object number 2 in the old generation, then when object number 2 tries to reference them, I stop object number 2 and say that, hey, I'm going to register you. I'm going to say that you actually are a parent of 3 and 5. So I'm just going to note that down. And once I've noted that down, when I'm doing a garbage collection in the Eden space, when I'm clearing out the babies, I'm going to be looking at 3 and 5 and saying that, okay, I need to look at the old guy, object number 2, to check whether you guys are still alive or not. That's the general idea. But the good thing here is that I'm not going through all the old people for references. I'm just going through a few objects which have references to the young region. So usually this is going to be something like maps, which are getting new objects into themselves. Okay, so map registration before an object can reference a young object is done through code injection in Java. There is something called JIT, just in time. So anytime an object tries to load a reference onto memory, so this is a write. In fact, we are going to be registering that write. And how is that happening? We have something like a Bloom filter, which is called a card table. You mark that part of memory which now has become dirty. So if you see here in the old generation, you have 4 blocks you can partition the old generation into 4 blocks, and partition number 3 has old object number 2, which is pointing to young generation objects. So what you can do then is in the card table, mark 3 as dirty. So all the objects in 3 have to be gone through for references in the young generation. So you say, okay, old object 2, tell me all your references. If you're pointing to the young generation, okay, those objects are now alive. Similar for old object number 5. So that is how we are kind of dealing with garbage collection in general. Okay, and just in time is going to be something that we'll be looking into multiple times in this presentation. Okay, now another motivation for garbage collectors is to reduce pause times. So they call this latency in a lot of places. If you have an application running, then what's going to happen is when the garbage collector kicks in, it completes this process of marking, doing the tricolor algorithm, and then clearing out all the objects, setting the data structures up. All this takes time. And during this time, if you are running an application like Amazon's shopping cart, someone comes with a request to add to cart, and then it takes 10 seconds because the garbage collector is running in that time. The request can time out. People will be upset because it's taking so much time. Your site feels slow. And if you're looking for like 99.99, all the SLAs that we have, latency numbers is something very important. So you want to reduce the maximum pause time of an application. That's a motivator for us. And one way to do that is to do things in slices, in pieces. So concurrency is the solution. How so? Well, you can time slice the amount of work you have to do. So let's say thread 1 gets 3 time slices in amongst all the time slices that you have in your application. So the garbage collector is going to be taking up 1 thread, or it's going to be running in concurrent, basically. Right, so that's the idea. But there's a problem. And the problem is that we have the mark sweep algorithm going this way. A goes to B, B goes to C. C says that, okay, I have no other outgoing references, mark me black. And then the app can wake up. If you have concurrency, then the GC is getting a time slice. All the work it could do was mark A, B as gray and C as black. And then it had to let go for the app to come in. And the app says, okay, assign a new object from D to F. So that's a new object. And then C also points to F. So this is all the application's work. Okay, and then D is no longer pointing to the object. So you deleted that reference. The weird thing here is that C has been completely processed. So when the GC wakes up, C is not going to be seen, right? On top of the stack, you had B, the pointer to B, the adjacent objects to B are C and D. So you go to D, you go to E, you mark it as black, and then the algorithm completes. But F should have been in your heap, but the garbage collector comes in, says that F is white, so we need to kick it out, and then we have a problem if you call that function. Okay, so this problem can be solved using the same concept as earlier. You have just in time. So anytime an object is about to be, a reference is about to be deleted from D, and you have the fact that a black object is pointing to a white object. So the general idea is that there's when you're doing a BFS or a DFS, you have a wave which flows outwards. So if you imagine the head of the wave, the front of the wave in a beach being colored gray, and the sea is black and the beach is white. Okay, so if the wave has already crossed you and then you start pointing to guys behind the wave, that's not allowed. That's the general idea. So we see that has happened. C is pointing to F. So the C is pointing to the beach without having a gray marker, without having the wave head in between. So what we need to do is fix that. So one of the ways to fix it will be to just add in a right barrier, mark it as gray. And then when the GC wakes up, it sees that F is on top of the stack. Let's mark it black. And then you continue with the algorithm and you have not lost any objects. So the lost object problem is solved this way. And with this, you have now concurrency. So things are going well. You can have your application running in time slices along with your garbage collector. Okay. So this brings us to the concurrent mark sweep garbage collector. This is what it does in general. This is how it collects objects in the old generation. The young generation still has stopped the world, but it's pretty good. Okay. I'll just wait a minute over here for questions so that in case you have any doubts in this, you can let me know. So George has a question. What is the best practice to make the GC to perform the best? Well, GCs are designed so that you have large allocations which are surviving for a short period of time. And that means that if you don't really need to worry how much you allocate as long as they're living for a short period of time. It's designed that way. Generational garbage collectors at least are designed that way. Recently, the problem that I showed you a little earlier about nepotism, old objects pointing to the new ones, that's a generational problem. So you have Shenandoah and ZJC, both of them at the moment are not generational collectors. So you can use them for, I guess, even long living objects and not face that much of an issue. But in general, if you're using CMS or G1 GC, I'd suggest short living objects are the best way to go forward. That's the generational hypothesis. Sana's asking, young, old, and permanent are the three generations. What if we needed another generation later on? I'm not very sure about that question, but young and old are the ones where garbage collection happens. Permanent used to be a place where usually classes used to be loaded, so you wouldn't expect them to be removed. Right now, I think G1 GC called it meta heap or something. Not too sure about that, but it seems like the problem has been reduced a lot. Meta space, yes. So it seems like the problem is not as severe anymore after ZJC has come along with I think concurrent class unloading also. So that's pretty interesting. Although I don't know if it's still on development or they have pushed it out. Yeah. What if we needed another generation later on? Well, it's like you take the generation hypothesis and you start breaking them by behaviors. So instead of 2 pieces, you have 4 pieces. But we are getting too application specific then. You can, at the end of the day, then start thinking about implementing your own garbage collector, or at least helping the garbage collector by saying that cron, every 3 minutes, kick these objects out. So Olaf, I'll take this as the final question, then we'll move forward. You said short-lived objects will not be a big problem for GC. Does this apply to modern GC algorithms or also JDK 7 and 8? So 7 to 8 has most of the algorithms which are based on the generation hypothesis. So short-lived objects are good. They aren't a big problem. But JDK 11 plus, yeah, the latency times have been reduced, have been almost constrained to, in ZJC, they are looking for sub-millisecond response times, or rather application pause times. And Shenandoah also has small application pause times. So you shouldn't have that much of an issue. If I remember Kafka, which is like a queue if you think of it, Kafka used to have off-heap. The memory model was off-heap primarily because they wanted to avoid a lot of GCs. So that problem has been reduced to some extent because of the newer garbage collection algorithms like Shenandoah and ZJC. And of course, you can always buy something from Azul, which is C4, if you're super interested. Okay, getting back. The problem with the concurrent mark and sweep garbage collector is that the memory at the end of the day gets fragmented. This might not be as big a problem as it seems initially, because if you have small objects which do tend to come up, you can fit them into these spaces. But there is wastage of memory when you are having memory fragmentation. It's going to look like Swiss cheese is an example, and you might remember defragmentation is something that we did in older computers so that we get a continuous space. So that's what we want. We want to compact all the objects into one space so that the rest of the objects can cleanly come in. So it's faster assignment and also better memory usage. But how do we do that? Well, G1GC tries to do this. And what it does is it partitions the heap into a few thousand regions, which is 2048, that is 2 raised to the power 11. It then marks each of these regions. So I'll just take a diagram. Marks each of these regions as either Eden or Survivor or Old. So there's also Humongous, but let's not get there. Eden, Survivor, Old are things that we have already looked into. We are going to be following the same algorithm of mark and sweep on these spaces. And once you have collected all the garbage, these spaces are going to have a lot of fragmentation inside them. So what you want to do is you want to compact these spaces into a single space. So maybe some Survivor objects need to be promoted to the old space. Maybe some old objects can be pushed into the new old space. All right, so this is a pretty revolutionary algorithm. This is very useful. In fact, until very recently, it came in, I think, JDK 8. So it's a very interesting algorithm. I won't be getting into too much detail over here. It has, like the card table that we talked about, it also has a remembered set, which tells you that there is inter-region pointers, right? And the compaction is over here. The biggest problem, compaction is stop the world. Another 2 points to notice here is that G1 stands for garbage first. So that means that it needs to have a counter of how many objects are alive in each space. So if you have a look over here, every space is going to be containing the number of pointers it has alive, the number of objects it has alive. And the spaces with the least number of live objects will be assumed to have the maximum amount of garbage. So that's why it's garbage first. And that's the heuristic it is using here. Okay, so we can do compaction, but compaction, like we said, is going to be a little slow because it's a stop the world event. Stop the world means that nothing's happening. The application is not going to run till I complete this job. Because if I let it run, then the application might mess up something that I'm doing right now. Okay, so what can we do about this? Concurrent compacting. That would be awesome. So here's a problem with concurrent compacting. I mean, concurrent compacting would have been done definitely if it was easy, but there's a problem. You have the application, you have it pointing to an object. So that is the headers are placed in the starting of the object. So the GC woke up, the GC says, okay, compact. So compacting means you push objects onto one side. So that is a move operation, which is a write operation. So that requires a copy. So the GC makes a copy onto another space. And because it is concurrent, the application can also wake up anytime. We don't know. It's like brain surgery happening or a split personality. Like we don't know, something just happened. And the application says, I don't know anything about a copy, but please change int a to 7, from -1 to 7. Now the GC wakes up and the GC says, I have made a copy, make the application point over here. So this is a problem. You have a lost write over here. So basically int a being marked as 7 is going to be lost. That is a lost update. Okay, and the way we are going to be solving this is something called a Brooks pointer. So right now you have the copies of the objects. You're going to be using something called a forwarding pointer. So anytime you access an object, you go to an object and you say, is this really the object that I'm looking for? So you go around 4 or 8 bytes back, you go to the forwarding pointer, and the forwarding pointer tells you the actual address of the object. So most of the times the forwarding pointer will be pointing to yourself, in which case you make the update in the object itself. But when the garbage collector is running and it can update this pointer to this new object. Okay, and we'll see exactly how this is happening. It's not the garbage collector technically that is doing this. It's when garbage collection is happening when this can happen. Right, and the application now indirectly through all this indirection is pointing to this new object out there, the copy of the object. And now it can make an update on this new object, int a equal to 7, life is fine. However, there is one problem. Garbage is collected. And by the way, this update of the forwarding pointer will happen through write barriers. Again, the just-in-time has to inject some code in Java so that the pointer manipulation can be handled. And there's some if-else conditions that, hey, is the garbage collector running? Is this in the collection set? And stuff like that. And has a copy been made? So based on that, it makes a decision. So let's see. We again come back to the original scenario. You need to update the value of a to 7. So the garbage collector is not going to be doing the job. It's like a discussion between a PM and an engineer. Oh, I'm sorry. I think we are running out of time. So I'll just quickly go through this, and then I'll take questions for the rest of the 2 minutes. You have 2 applications trying to update the same object. They're going to be making copies by themselves. So that is the code that has been injected by the just-in-time. And one of them will succeed. Why is that? Because before it makes the update on these copies, it actually tries to update the forwarding pointer. Now, only one person can win. So we do an optimistic lock of compare and swap, which means that one application, let's say the upper application wins, it updates the value to 7. And then the application below is going to be, before making this update to its own copy, it's going to be checking that, hey, did I win that race? No? Okay. just use the copy that the forwarding pointer is pointing to and update that to 20. And the garbage is collected. Okay, this is how the concurrent compacting will happen. That's the concurrent writes happening, and we are taking care of that. So this is how it works in Shenandoah. Like I said, ZJC is not something I've touched because it took me 43 minutes to get here. But if you're interested in that, maybe I'll take that on my YouTube channel later on. You have the generational hypothesis. The conclusion is that generational hypothesis holds in most cases. Concurrency reduces pause times. That's good. We want it as much as possible with some exceptions. If you want throughput to be high, then just go for a parallel garbage collector. Life's simple. And finally, compaction is good-ish. Compaction has its own overhead, but it seems like overall it's good. G1GC has proven that compaction in many applications is good. We are done with the presentation, and see you guys. Goodbye.